So welcome back. So we were discussing about the extrusion deformation mechanism in extrusion process. So in this class we will start with the wire drawing process. So as we have discussed before, so it is has wire drawing has a quite a lot of similarity with the direct extrusion process. So so you can in this slide you can see. So this like we have discussed in the earlier class. So this is a typical case of hollow extrusion. So where you can see this mandrel is basically piercing the billet, the workpiece billet, and then that is responsible for creating the hollow in the billet, and then this ram is basically pressing it through the die so that the this cross sectional area, the thickness region of the hollow pipe can be developed. So similar concept has been generally considered in case of wire drawing, although in case of wire drawing the idea is not to get a hollow object, rather to get a solid object, or more precisely a solid wire. So then in this case the metal is pulled through a die via tensile force with most plastic flow caused by compression. So the drawing can involve bars, rods, wires and tubes. Tube sinking refers to drawing a hollow tube without a mandrel, while tube drawing uses a mandrel for internal support. So these processes are usually performed at room temperature but can cause temperature rises due to the large deformation involved. So so this is a typical schematic of the wire drawing process, where you can see so this coil, this workpiece coil is fed through this conical die entry, and where from it is pulled by a bull block, and then the cross sectional reduction of this coil takes place and the wire can be made. So as by changing the opening in this conical shaped die, the cross sectional area or the diameter of the resulting wire can be changed. So so then it is not necessarily that it is always should be a circular cross section to the drawn wire. It can be rectangular as well, depending on the particular application. So the principles of bar, rod and wire drawing. So the principles of drawing are similar for bars, rods and wires, but the equipment differs based on the size of the product. Rods and tubes which cannot be coiled are processed on draw benches, where the rod is pointed, inserted through a die and pulled by a hydraulic or chain driven draw head. So draw speeds ranges from 150 to 1500 millimeter per second. So draw bench setup. So on a draw bench the rod is clamped to a draw head, and which moves along a run out of up to 30 meters, exerting forces as high as 1 meganewton. So this setup is designed for straight drawing of rods and tubes. Conical drawing die. So the cross section of a conical die has three important regions. So entrance, that is the bell region, shaped to draw lubricant into the die, promoting smoother wire drawing. So yeah, so you can understand from this schematic. So this is the bell region, which is the entrance region of the wire drawing conical wire drawing die. So it is safe to draw lubricant into the die, promoting smoother wire drawing. So after the bell section, then this is the approach angle. So then this is a most vital region. So this angle which determines the amount of strain imparted on the workpiece rod or billet, which is undergoing the wire drawing process, and also this approach angle, which is also mentioned earlier in case of extrusion as the semi die angle, which determines the area ratio of extrusion, or also in case of wire drawing. So this section where diameter reduction happens, with the half die angle alpha being the critical parameter for controlling deformation. And then there comes the bearing region. So then bearing region is the region which is marked over here. So then no diameter reduction happens here, but it controls friction and can be refinished without altering the die's exit dimensions. Then finally another important section of the wire drawing die, that is back relief, where actually there is a enlargement of diameter happens. So then so this section allows for slight expansion of the metal after it exits the die, reducing abrasion risk and ensuring smoother flow if drawing stops. And also this back relief is very much useful to reduce the chances of residual stress development within the drawn wear, and thereby it also allows the drawn wear to be used in practical purposes. Materials for dies. So, the drawing dies are typically made from cemented carbide or industrial diamond for fine wears. So, the die nib where the drawing takes place. So, the die nib is encased in a thick steel casing to protect it from damage. Okay. So, this is the material. So, the neglect of friction and deformation. So, the equation so here you can see so there are two factors. So, in this equation which is which is it is so the equation can be developed where we can be these factors like friction can be neglected in the drawing process. So, the friction, the influence of friction between the material and the die can be ignored, and also to simplify the expression, and the transverse stresses and redundant deformation. So, the effects of transverse stresses and internal shearing, that is redundant deformation, can also be neglected, which would typically impact the drawing force. So, the strip drawing with Coulomb friction. So, in strip drawing, the presence of a Coulomb friction coefficient mu between the strip and the die is introduced. So, this friction creates a frictional stress mu p that opposes the motion of the strip through the die, which is which can be clear from the schematic. So, this is the frictional stress, that is mu p, which opposes the movement of the wear through the conical die, and this is the pressure which is exerted by the die to the workpiece which is undergoing wear drawing process. So, the equilibrium equation to balance along the x direction can be written as sigma x into dh plus h d sigma x plus 2 p tan alpha dx plus 2 mu p dx. So, why 2 mu p? Because it is applicable on both the top and the bottom side. So, that is why 2 mu p dx, which is equal to 0. So, it includes friction mu and geometry, that is die angle or semi die angle alpha. So, the yield condition sigma x plus p is equal to sigma 0 prime and flow stress in plane strain. And B is equal to mu cot alpha, which incorporates friction and semi die angle alpha. So, then the differential equation is so d sigma x by so if we can rearrange the terms from this equation 1 to equation then we can arrive at the equation 2. So, then d sigma x by sigma x b. So, where b is equal to mu cot alpha. So, incorporating that into the equation 1. So, d sigma x by sigma x b minus sigma 0 prime into 1 plus b. So, sigma 0 prime we are introducing here because sigma 0 prime is equal to sigma x plus p. So, is equal to so dh by h. So, so this can be integrated to solve for the draw stress, and the resultant expression of the draw stress comes as sigma x a is equal to sigma 0 prime 1 plus b by b into 1 minus h a by h b to the power b. So, here so this is a expression of the draw stress which includes the consideration of the friction between the this die and the workpiece workpiece which is undergoing wear drawing, where h a and h b are the initial and the final heights of the strip. So, which is shown over here. So, so then so here you can see that here it is slightly mistaken here. So, please correct it. So, here HB is the initial height of the workpiece and HA is the final height of the workpiece, as in you can understand it from this schematic drawn over here. So, this is the reduction of the height of the workpiece or the strip is happening, that is reduction is happening from HB to HA by wire drawing process. So, So, frictional stress effect. So, the friction stress mu p acts as a resistance to the wire drawing process, working against the strip's movement and increasing the required drawing force. So, equilibrium in the x direction. So, then the equilibrium of forces in the x direction is analyzed to understand the influence of friction on the strip drawing process. So, the balance of forces considers how friction impacts the overall mechanical behavior during the drawing process. So, here sigma x a is equal to sigma 0 into ln a 0 by a is equal to sigma 0 ln 1 by 1 minus r. So, here you can see that AB is the initial cross sectional area and AA is the final cross sectional area in case of wire drawing. So, here this is the expression of the draw stress which does not consider the effect of friction. So, which is a gross simplification of the calculation of the draw stress. So, where it is only the as we have known earlier how we are writing it like this. So, as we have known that area ratio R is equal to A 0 minus A f by A 0. So, initial minus final area divided by the initial area. So, 1 minus A f by A 0. So, that means A f by A 0 is equal to 1 minus R, 1 minus R. So, then A 0 by A f is equal to 1 by 1 minus R. Okay. So, then here we can write it because here it is so the initial by final area. So, it is the final area is A and the initial area here. So, final area is A as per this schematic and the initial area A 0 is A b, which is you can understand from here. So, that is why we can write that sigma x a is equal to sigma 0 ln 1 by 1 minus r. Whereas, when we are considering the effect of friction which is analogous to the expression we have just discussed in the previous slide. So, you can see, so in spite of height of the strip, now we are talking about the diameter of the wire. So, then sigma x a is equal to sigma 0 1 plus b by b. So, b is equal to mu cot alpha that we have discussed earlier. So, this is to consider the effect of the friction into 1 minus dA by dB to the power 2b. So, a similar but slightly different analysis for wire drawing with friction is given by Johnson and Rowe. So, where the surface area of contact between the wire and the die is given as S is equal to AB minus AA by sin alpha. So, that means S is equal to AB, that is the initial area, minus final area divided by sin alpha, that is the semi die angle. So, sine of the semi die angle. So, which is the surface area S, and then so forces in axial direction. So, the draw force PD is balanced by the horizontal component of the frictional force and the horizontal component of the normal pressure. So, the draw force formula with friction becomes, in this case for PD is equal to mu p bar S into cos alpha plus p bar S into sin alpha, where S is the surface area that we have already calculated as AB minus AA by sin alpha. So, this is the resultant expression for the draw stress. So, this can be expressed as PD is equal to p bar into putting the expression for S that we have just discussed in the previous slide. So, that is AB minus AA by sin alpha. So, then p bar into AB minus AA by sin alpha and then mu cos alpha plus sin alpha, because here also if you just take the p bar S common. So, p bar S if you take common, then it becomes mu cos alpha plus sin alpha, and then if you just put the expression for S. So, then it becomes p bar into AB, that is the initial area minus final area divided by the sine of the semi die angle into mu cos alpha plus sin alpha. So, this is the expression for the die pressure PD. Okay. So, where mu is the coefficient of friction, p bar is the mean normal pressure, and AB and AA are the billets areas before and after drawing. So, the simplified formula in the absence of friction. So, if there is no friction, then B is equal to 0. So, that means the equation simplifies to PD is equal to p bar AB minus AA. Why it is so? So, because friction not there, B is equal to 0 means mu is equal to 0. So, then mu, if mu is equal to 0 means, then it becomes so this expression of PD, that is die pressure, becomes equal to p bar AB minus AA divided by sin alpha into, so mu is equal to 0. If it becomes equal to 0, then it becomes sin alpha. So, sin alpha gets cancelled and then the resultant expression becomes this. So, that is written over here. P d is equal to P bar, that is the average normal pressure, mean normal pressure into A b minus A a. So, which is equal to again sigma 0 bar A a ln A 0 by A. So, this is how so the draw stress with friction. So, the draw stress sigma x a accounting for friction is given by sigma x a is equal to P d by A a. So, that means as we have got the expression for P d, that is the draw the die pressure is equal to sigma 0 bar A a into ln A 0 by A a. So, then so it is the basically the initial area by final area A 0, or it can be also be written as A b. So, is equal to sigma 0 bar ln. So, because A gets cancelled, the final area at the bottom, because we are dividing by the final area. So, it gets cancelled with this, and then sigma 0 bar ln A 0 by A into 1 plus B. So, this is the draw stress with friction. Okay. So, this is the expression of draw stress without so this is the expression for die pressure without considering friction, and as we know that when the friction exists, so then it will become like this. So, how it is becoming like this? If you are dividing by sin alpha, so then sin alpha if you divide, then cos alpha by sin alpha, that means mu cot alpha plus 1, that means 1 plus b, because as we know that b is equal to mu cot alpha. So, then directly we are getting this expression. So, then this expression gets modified, the die pressure in case of friction consideration gets modified as P bar A b minus A a into 1 plus b, because so 1 plus mu cot alpha, which is mu cot alpha is equal to b. So, 1 plus b, and then if you are dividing it by A a, so then so if you are coming to this expression, so then it is basically sigma 0 bar A a into ln A 0 by A a into 1 plus b. Okay. So, then this A gets cancelled out when we are calculating the draw stress with friction, and then the resultant expression becomes this sigma 0 bar into ln A 0 by A into 1 by 1 plus b. So, this is the expression written over here, where b accounts for the friction's effect. Okay. So, the equation includes terms for uniform deformation energy and frictional energy. So, both energy types are important in understanding the total energy required for drawing processes. So, the redundant deformation refers to the unnecessary internal shearing that raises the material's flow stress, but does not contribute directly to the dimensional change. To account for this, a factor phi is introduced, which adjusts for the influence of redundant deformation. So, the modified draw stress expression becomes sigma x a is equal to sigma 0 bar ln A a by A b into 1 plus b, which is multiplied with the factor phi, which is a factor introduced to redundant deformation. So, you can see, so we have first introduced how to calculate the die pressure and also the draw stress without considering friction. Then we have introduced the concept of friction at the die wall with the workpiece, and then the term B is equal to mu cot alpha got introduced into the die pressure. Mu cot alpha got introduced into the die pressure and the draw stress expression, and then next we are introducing the case of redundant deformation. So, so then which is expressed here with the factor phi. So, then this is the final expression of the draw stress which is applicable in case of wire drawing. So, this equation adjusts the flow stress sigma 0 bar for the effects of redundant deformation as well as friction. So, the practical implications, so the inclusion of redundant deformation in the stress calculation helps providing a more accurate estimate of the draw stress necessary to perform the wire drawing of that particular material, especially for materials where internal shearing is significant and the losses analogous to the internal shearing is significant. So, that is why this expression given at the top gives the complete overall understanding of the draw stress calculation in real life application. So, the flow curve of drawn wire is superimposed on the flow curve of annealed metal, and the shift along the strain axis reflects the drawing reduction, that is epsilon asterisk is equal to ln AB by AA, that means ln final area, initial area by final area. So, as I have mentioned numerous times, that initial area by final area is equal to 1 by 1 minus r. R is the thickness, area reduction, that is A0 minus A by A0. So, that is the, so that means the, so the drawing reduction, so the so then epsilon asterisk becomes equal to ln into 1 by 1 minus r. So, this shift shows the redundant work which increases the yield stress of the drawn material. So, this is also the reason you can understand, where you please recall that earlier we have discussed, when we were discussing about the offset forging, about keeping the this flash. So, that flash we have discussed that flash also facilitates complete filling of the die material, complete filling of the die cavity by the workpiece material to achieve the desired shape of the component made. Because this, because of the concept of redundant deformation, the applied forging pressure is also increases. The similar is the concept that is applicable in case of wire drawing as well, and because of that redundant work increases the flow stress of the material. So, the which is undergoing the wire drawing process. So, the flow curve shifts to a new strain value, that is epsilon asterisk. So, the area between the basic and the shifted flow curves represent redundant work per unit volume. So, the upper bound analysis accounts for redundant deformation by assuming simple deformation regions. So, this leads to complex equations for draw stress considering friction, die geometry and material properties. So, the revised draw stress expression for wire drawing can be given as sigma x A is equal to sigma 0, neglect this one. So, that is the flow stress sigma 0 into 2 f alpha ln R A by R B. R A by R B, so R B is nothing but the radius of the initial billet, and R A is the radius of the final extruded or wire drawn billet, plus 2 by root 3 alpha by sin square alpha minus cot alpha plus 2 mu cot alpha into 1 minus ln R B by R A into ln R B by R A plus L by R A. So, this is a complicated expression which considers for various factors influencing draw stress, including friction and geometric parameters. So, if not asked, otherwise you need not to include consider this expression, rather you can consider the expression which we have discussed previously. So, yeah, so you can consider this expression and that is enough. So, there is no need to consider the effect of die geometry parameters unless otherwise stated. So, now we can go to the even simplified expression for draw stress. So, that sigma x A, which includes a redundant work term. So, sigma x A is equal to sigma 0 into 1 plus m by 2 sin 2 alpha into ln R B by R A plus 2 by 3 tan alpha, where m is the friction factor, alpha is the approach or semi die angle, R B and R A are the billet and wire radii. Okay. So, R A is the radii of the wire, which is the resultant wire drawn wire, and R B is the initial diameter radius of the workpiece billet, which is undergoing wire drawing process. So, the deformation zone geometry, coming to the deformation zone geometry, it provides a method for treating redundant work. So, for round wire, delta is equal to alpha by r into 1 plus 1 minus r to the power half to whole square. So, where r is the drawing reduction. Okay. Commercial wire drawing typically uses alpha approach or semi die angle in the range of 6 degree to 10 degree. Drawing reductions are about 20% and the value delta values typically ranges between 2 to 3. So, the relation between redundant work and delta. So, higher delta values correspond to lower drawing reductions and higher die angles. So, this is an interesting thing that you should consider. So, higher delta values correspond to lower drawing reductions and higher die angles, whereas lower delta values correspond to higher drawing reductions and lower die angles. So, they are like counter productive to each other. That means, if you increase the higher die angle, so it leads to lower die drawing reductions when the values of delta is high, when the values of delta is low, then lower die angle will lead to higher drawing reductions. So, the experimental data shows that the redundant work factor is related to delta. So, this highlights the influence of deformation zone geometry and drawing reduction on redundant work. So, then if we discuss the case of cold drawing of hollow cylinders. So, hollow cylinders or tubes produced through hot forming processes like extrusion or piercing and rolling are often cold finished by drawing. Cold drawing is used to improve dimensional tolerances, surface finish and mechanical properties through strain hardening. So, it allows to produce tubes with thinner walls, smaller diameters and irregular shapes. So, the advantages of cold drawing. It produces tubes with better dimensional accuracy and surface finish than hot forming method because of the strain hardening, and enhances the and also preferential flow of grains. So, enhance the mechanical properties of the material especially by increasing hardness, and again it is because of due to strain hardening, and that is also the reason of increasing hardness as well as strength, and allows to produce thinner wall tubes or tubes with smaller diameters than are achievable with hot forming processes. So, here this is a typical example of tube drawing processes, tube drawing with where we are not considering any mandrel to support the inner surface of the tube, then it is called as tube sinking. So, this is A, and then when we are using fixed plug and then we are drawing the tube or reducing the thickness of the tube, hollow tube by this cold drawing technique, then it is a we generally utilize fixed plug that is shown in figure B, and then this is a typical case of floating plug where it is useful to optimize the thickness reductions at the region where it is the section is going through the die, the conical die or the converging where the tube the hollow tube changes its cross section. And then the fourth case is moving mandrel, where this so this is the best case scenario where the surface finish, that means the surface finish of the hollow tube at the inner surface can be achieved to the best compared to any other condition like tube sinking or with fixed or floating plug, that is shown in A, B and C. So, the best case scenario is D. So, when we are doing the tube drawing, cold drawing of tube, hollow tubes by moving mandrel with the help of moving mandrel. So, going ahead with the tube drawing process. So, tube sinking, as we have discussed in the previous slides, it has no internal support for the tube during drawing, results in wall thickening and uneven internal surfaces. Redundant strain is higher due to significant shearing at the die's entry and exit. Limiting deformation is lower compared to other tube forming processes. And then plug drawing, when we are doing the cold working or cold drawing of hollow tubes with the help of a fixed plug, that is analogous to figure B that we have shown over here. So, then a plug supports the inside of the tube during the drawing process, allowing for control of both inner and outer surfaces. It produces tubes with more consistent dimensions than can be achieved in case of tube sinking, and also with better surface attributes compared to tube sinking technique. Key factors in tube drawing is redundant strain, so higher in tube sinking due to shearing effects, which limits the amount of deformation the tube can undergo, and the deformation control. So, in plug drawing, both the inner and outer diameters are controlled, which improves the overall quality of the drawn tube, cold drawn tube. Okay. So, the tube drawing with plug or mandrel, that is the best case scenario with moving mandrel. So, in tube drawing with a plug or mandrel, most of the deformation occurs due to reduction in wall thickness. So, the inside diameter of the tube is slightly reduced to allow for the insertion of the plug or mandrel before drawing. So, since there is no hoop strain, the analysis can be simplified using plane strain conditions. So, in case of tube drawing with a plug, the draw stress sigma xa can be explained as, so again which is analogous but slightly different than the draw stress expression that we have discussed earlier in case of wire drawing. So here sigma xa is equal to sigma 0, that is the flow stress of the material, into 1 plus b prime by b prime into 1 minus ha by hb to the power b prime. So here b prime is considered due to the friction. So here b prime accounts for friction effects at the both the die tube, so and also the mandrel tube interface. So here there are two interfaces, so that's why the effect of friction is more predominant. So here you can see this is one surface, so that means between the die and the workpiece there is one friction, say mu 1, and then there is another friction between the mandrel and the inner surface of the hollow tube. So this is another interface, say the friction coefficient at that interface, say can be termed as mu 2. So then there are two kinds of friction. So like I have shown you, it is the mu 1 is the coefficient of friction between the tube and the die wall. So that is shown here, tube and the die wall. So that is mu 1, and then mu 2 is the coefficient of friction between the tube and plug or mandrel. Okay. So the alpha is the semicone angle of the die, beta is the semicone angle of the plug, which is 0 for a cylindrical plug. So this is the expression for tube drawing with a plug or mandrel, and the effect of moving mandrel. So in tube drawing with a moving mandrel, the frictional forces at the die tube interface act toward the die entrance, similar to wire drawing. However, the frictional forces at the mandrel tube interface act toward the exit of the die, which changes the overall stress and friction distribution. Friction adjustment in stress calculation. So for a moving mandrel, the value of b prime must be adjusted to account for the friction forces acting in opposite directions at the die tube and mandrel tube interfaces. Why they are acting in the opposite direction, as discussed at the top. So because the friction forces at die tube interface act toward the die entrance, whereas frictional forces at the mandrel tube interface act toward the exit. So that's why they are acting opposite direction to each other. So ensuring the accuracy of the draw stress calculation, that is what we have discussed here in this slide. So then so the differential equation for equilibrium. So the differential equation for equilibrium in case of ideal homogeneous deformation is h d sigma x plus p dh is equal to 0. So this integrates directly to describe the stress distribution during deformation, and if the friction coefficient at the mandrel mu 2 exceeds that at the die and the tube interface, hollow tube interface mu 1, so B can become negative. This results in a draw stress lower than that required for frictionless ideal deformation, indicating the impact of frictional forces in tube drawing. And tube sinking process. So tube sinking involves the reduction of the inside diameter of the tube without internal support from a mandrel, and that is also a reason that the inside surface of the tube generally assumes unwaviness, and the surface finish that can be achieved in the internal surface of the tube in case of tube sinking is much poor than we can achieve with the help of a fixed or moving or plug or mandrel. And then so this process reduces both the inner diameter and the wall thickness of the tube, and the reduction in inside diameter is part of the tube drawing process. So this is the case of tube sinking. So in case of tube sinking, there is a slight variation in the draw stress, which takes the form sigma xa is equal to sigma 0 double prime into 1 plus b by b into 1 minus a by ab to the power b. So here sigma 0 double prime is the yield stress adjusted to account for the complex stresses evolves during tube sinking. So stress assumptions in tube sinking. So the draw stress equation for tube sinking is analogous to that for wire drawing, but accounts for the specific geometric properties of tube such as mid radius and also the wall thickness h. So cross sectional area reduction. So the cross sectional area of the tube is related to the mid radius and wall thickness as A equivalent to 2 pi r h into A. So here I mean so this helps in relating the geometric properties of the tube to the stresses originates during drawing. So the residual stress patterns based on reduction. So the two types of residual stresses arise depending on the percentage of reduction per pass in cold drawing. So residual stresses distribution changes when reduction exceeds a threshold 1%, and small reduction, that is even lower than 1%. So it generates longitudinal stresses which is compressive at the surface and tensile at the axis, and then radial stresses tensile at the axis and 0 at the surface, circumferential stresses which follows the longitudinal stress pattern, that is compressive at the surface and tensile at the axis. And in case of large reduction, that is greater than 1%, like we see in industrial parlance. So then longitudinal stresses are tensile at the surface and compressive at the axis. So you can see a totally contrasting finding when we are dealing with small reduction and when we are dealing with large reduction. And then in case of radial stresses, again it is the exactly the opposite that we have discussed in case of small reduction. So here it is compressive at the axis and 0 at the surface, and circumferential stresses also the exact opposite, because in case of both small as well as large reduction, circumferential stresses follows the same trend as of longitudinal stresses that we have discussed before. And now coming to the localized deformation in surface layer. So the first type of residual stress pattern is common when deformation is localized in the surface layers, like in light cold drawing. Impact of residual stresses. So these residual stresses significantly influences mechanical properties like fatigue strength, corrosion resistance and overall structural integrity of the cold drawn wires and rods. Okay. So then the impact of die angle and reduction on residual stresses. So longitudinal residual stress in cold drawn brass wire increases with the half die angle for a given reduction. So maximum residual stress occurs in the 15% to 35% reduction range. So these are basically the findings, that empirical findings that has been listed here, which is observed with rigorous experimentation. And so this has which has transformed to become a thumb rules for the particular processes. And then residual stress distribution in sunk tubes. So for tubes produced by tube sinking, the longitudinal residual stresses are tensile on the outer surface and compressive on the inner surface, and the circumferential stresses follow the same pattern as of longitudinal stresses, like we have discussed earlier also. So and and radial stresses becomes negligible, and the relationship with cold work and yield stress. So the circumferential stresses on the outer surface of the tube increases with reduction in diameter at the same rate as the increase in yield stress due to cold work. So this is about the wire drawing and also about cold drawing of tubes by sinking or with the help of fixed or floating plug and mandrel. So with this we are done with the metal forming module of this course, and we will meet again with the next module in the next class. So till then, thank you.